Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside, and we are going to be going to Chapter 3 of the Big Ideas Math Integrated Math 2 textbook. This is all about graphing polynomials. Now, we just came off of Chapter 2 of factoring polynomials. We started with distribution and naming polynomials and things like that. Now we're getting deep into, sorry, I just said polynomials, quadratics. We're going to be graphing quadratics, these U-shaped curves, upward, downward, parabolas, and all features of them. And they go kind of slowly through them. I'll be honest, this isn't generally the way that I would progress through it, but I'm going to go through it in the section order. You can jump whichever way your teachers teach it. If it were up to me, I'd actually teach Chapter 4 first on solving all kinds of quadratics, not just through factoring, but through other means before I went to here. But this is fine. The way that the book actually led you into it in Chapter 2, talking about the zeros representing the intercepts, or the roots representing the x-intercepts of your polynomials, is actually a pretty good jumpstart into what these things are. We're just going to look at a bunch of factoring forms. Now, this is section 3.1. Section 3.1 is just on graphing the function f of x equals ax squared. So there's only one parameter, which is known as a vertical stretch factor, and a reflection component, the way that this thing can go upward or downward as a U-shaped graph. So we're going to take a look at that. And then section 3.2 has a vertical shift component to it. Section 3.3 has a horizontal shift component to it, but it's a different form, sort of. I mean, you're going to see, but again, that's why the evolution is kind of strange. But as long as I go through how they teach it, for the most part, then that'll be fine. At some point, well, probably even starting in section 3.2, if they keep talking more about use a table, I'm going to be doing a lot less table work. Even on this one, I'm going to be doing a lot less table work outside of just computing how these things go. So hopefully you can follow what I say based on what they do with the table stuff, or use the book itself, or use your teacher. However, this is my video, this is my channel. I just use their stuff as a template, Big Ideas Math, which is very good information, but hopefully that they work more in the form of what it means to use the transformations of the function of a parabola, and then we get to move forward with that. Because once I hit section 3.4, I think it is, you're on your own if you're following the book and if they're still using a table, because I'm absolutely not using a table at that point. There's a reason we have a form, and I intend on using that particular vertex form very much like we did for absolute value functions. With that being said, guys, I'm going to go ahead and move on forward. So we're going to look at what they do with examples and notes and all that stuff before we move into the actual problem set, which I think is only 31 problems, but because we have to graph and describe transformations and stuff, I assume it might be a little bit, so we'll see. Okay, we are going to identify characteristics of quadratic functions. I guess that means based on the graph, where's the vertex, the axis of symmetry, like all these words right here. Vertex, axis of symmetry, talk about domain and range, whether it's reflected, all that kind of stuff. And graph and use quadratic functions in this form, f of x equals ax squared. Now, there's only one parameter, which is a. The x squared is something you're just going to see throughout the entire chapter and throughout all of Chapter 4, and we saw it on a lot of Chapter 3, obviously, as well, when it came to factoring. So, let's identify characteristics of quadratic functions. A quadratic function is a non-linear function, that means it's not straight, can be written in the standard form y equals ax squared plus bx plus c, where a cannot equal 0. Listen, imagine if a equaled 0, 0 times x squared would be like that, and then it would become linear. So clearly a has to be a non-zero value, otherwise it's not quadratic. Now b and c, notice they didn't say b and c can't be 0, and in fact, since we're only using ax squared here today, b and c are going to be 0. We're not going to be talking about how these manipulate our graph or our equation or something like that in this particular section. The U-shaped graph of the quadratic function is called a parabola. In this lesson, you will graph quadratic functions where b and c, here we go, where b and c equal 0. So they mentioned a U-shaped graph. If we go ahead and take a look at this thing right here, it's got that U context. Now, very specifically, these are very specific points, right? You'd have to actually find out what those points are and such. It's not just, hey, draw U, but this thing actually, it never actually angles. It's not a V. It's not an absolute value. It doesn't have a slope. It's always curving at every point during this, and it sharpens itself more and more over time. Never goes fully vertical. They're probably going to talk about domain and range, and I get it there. The parent quadratic function is f of x equals x squared. Notice that the a value is now just 1x squared, so no transformations on that guy, and a positive one at that. The graphs of all the quadratic functions are transformations of the graph of the parent quadratic function. So anything else that is an x squared function where it's not a is 1, b is 0, c is 0, is considered to be transformed, whether it's stretched, compressed, reflected, translated horizontally, vertically, whatever it is. The lowest point on a parabola that opens up, like this, or the highest point on a parabola that opens down is the vertex. So here's the lowest point of an open up, and here's the highest point of an open down. The vertex of the graph of f of x equals x squared is 0, 0. So that's this. It's at the origin, non-transformed, and when we see it move left, right, up, and down in future sections, then the vertex will be in a different spot. It'll still be considered its lowest or highest point, but it will no longer be on the origin. It'll be transformed. The vertical line that divides the parabola into two symmetric parts is the axis of symmetry. So you see this dotted line right here. It's not, just like an asymptote. It's not like an asymptote, but just like an asymptote, the dotted line are not points on the graph, but they help describe how you find points on the graph. If you notice, the name is called axis of symmetry. Symmetry meaning because all parabolas have symmetry to them for x squared graphs. The same distance to the left side and right side at the same height means you have symmetry. Just like my face is symmetrical, like that kind of thing. So there's symmetry on here, and we can always draw them, and we can figure out what they are. For the graph of f of x equals x squared, the axis of symmetry is the y-axis, or the line x equals 0. Notice the axis of symmetry will always, I'm going to call it AOS, it's always going to have an x equals equation for these particular things because x equals equations are vertical lines. So when we're describing where the axis of symmetry is, we're describing what the line is that forms symmetry to the left and right side of the graph. In this case, it's on the y-axis, x equals 0. Here's x equals 1, 2, 3, 4, things like that. All right, they're giving us parent function behavior. They're letting us know what this looks like when it faces upward. Oh, and also notice that they mention when this is decreasing and increasing. We're asking what the y values are doing as we move to the right on x. As we go right on x, the graph is decreasing over here when x is less than 0. When x is greater than 0, the graph is increasing. Right there, the y values are going up. And at 0, it's hit its vertex. It's neither nor. It's just plateaued. It's flattened out. Okay, identifying characteristics. So let's see what different things they're going to want us to mention. We are going to consider the graph, whatever it is, even if they don't give us an ax squared graph, they're just going to say, based on the graph, can you tell me the characteristics? So that's a nice way for them to slow it down. They're saying, let's just talk about what quadratics are in general. Despite an equation, let's look at the graph. Let's describe it. Let's make sure we know what all the words mean. Domain range, increasing, decreasing, vertex, all that. An axis of symmetry. Using the graph, you can identify the characteristics such as the vertex, axis of symmetry, and the behavior of the graph as shown. So we can see when it's decreasing to increasing, and we can actually say that with these guys right here. Inequalities. We can state increase, decrease. So notice that it's decreasing when x is less than -1. Here's when x is -1, and it's decreasing when it's less than. It's increasing when x is more than -1. The domain's all real numbers. Here's the thing. Quadratics, you can plug in anything into y equals x squared or any equation of that sort. You're going to get a y value out. So this graph may go up forever. That's fantastic. But it also goes right forever, and it also goes left forever. The domain's all real numbers. The range is limited, however. The range is limited by a lowest point for an right side up facing graph. The range is every number greater than or equal to -2. When y is -2, everything above it is the range. And we've spoken a lot about domain and range in the past. I'm not going to get deep into what domain and range is. We're just using the characteristics here. And we can also talk about the axis of symmetry. X equals -1. It's this vertical line at -1 for x. It's going to be the same as the vertex x value, and the vertex is that lowest point that's -1, -2. I probably said that all out of order. Like, it was probably easier to say that in a different order, but that's just where I went to. That's where my mind went to. So there's 1, 2, 3, 4 things we can mention. Vertex, axis of symmetry, increasing, decreasing, and domain and range. Domain and range. So I'm going to try and keep those in mind if we get questions on those outside of the examples. But I wanted to show you, here's an upside down facing graph, which means the vertex is the highest point, and that means it's increasing here and decreasing there. And we can draw our own axis of symmetry, yada, yada, yada. So we're going to do that on future problems when they give them to us. Okay. Now, they say, remember, the graph of y equals a times f of x is a vertical stretch or shrink by the factor. So yes, a represents a vertical stretch factor. It can stretch or compress your graph, much like absolute value graphs did. If you guys recall, we'd have an absolute value graph that's v-shaped like this, and when a was greater than 1, you're multiplying by your y values by something bigger, which means it'll grow. It might look like that. That is known as a vertical stretch, because everything is taller. It's taller. than it was before. And if everything is a little less than, A is like less than 1 like this, it can be a vertical compression or vertical shrink, as they say. Like 1/2, you compress it more vertically. The domain's all real numbers. It goes forever left and right. We're talking about how tall it goes with respect to those x values. So they're doing the same thing here. If you notice the one in blue, here shows when a equals 1, and hopefully you can see this. The one in green is when a is greater than 1. Now you're, instead of multiplying by 1, you're multiplying, say, by 4. And when a is between 0 and 1, you're multiplying, say, by 1/4 or 1/2 or whatever, and it's a vertical compression. They all go up forever. But with respect to any certain specific x value, these y values are all different in comparison, where one is a stretch, one is a shrink, and they move on from there. When a is less than 1, this graph reflects over the x-axis, such as this. So when a equals -1, it's just flipped over. You can see the origin is still, the vertex is still in the origin. When a is less than -1, I kind of say greater than, in that way, it's a bigger number, larger negative. It still stretches, but it's reflected. And when a is between 0 and 1, but negative, it's a vertical compression, but still reflected over the x-axis. Okay, here's an example where they ask you to draw the graph and compare to the original parent function y equals x squared. So if you want to do this, it's all about order of operations. Substitute values in for x, some negative, some positive, and 0. And specifically when it's just ax squared, just do that. Some negative, some positive, and some 0. And 0, I should say, because 0 is your vertex. 0, 0 in this case. It's going to be your vertex for these particular problems. That's why we're going to work nice and slowly through them. But you got to use order of operations. When I substitute in 1, that's 2 times 1 squared. I first do 1 squared, which is 1, then times 2 is 2. 2 times 2 squared. I first do 2 squared, which is 4, times 2 is 8. You do not do 2 times 2 first. You do not do 2 times 1 first. You just got to make sure you follow the order of operations. Now, just like absolute values, when you square a number, it turns positive, and that's why the U shape comes into form. Like a V shape, it comes off its vertex. We've spoken about vertexes before, I just realized that. On V-shaped graphs, it would go off the vertex and would go positive in both directions because the absolute value of a negative is still a positive, much like squaring it is. So what makes this a U-shape instead of a V-shape? The fact that 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, that as I increase x by 1, a constant amount, the y values do not increase by a constant amount. They increase more over time. So there is a gradual increase of your values on y, just as x goes over 1 more each time. They're still symmetrical. They still have an axis of symmetry. So do absolute value graphs, by the way. But there's a gradual increase, which is why it never has a single slope. So for me, I'm always going to plot as many points as I can fit. For me, I'm not even really going to use the table, so to speak. What I'm going to do is focus more on numbers like these. 1, 4, 9, 16. You want to know your perfect squares. You want to know what 1 squared is, 2 squared is, 3 squared. However far you go over, you go up these amounts. When I go over x amounts, 1, 2, 3, 4, I go up 1, 4, 9, 16. From the vertex. 16 up when you're 4 over from the vertex, things like that. But the a value of 2 vertically stretches those numbers. Check this out. 1 times 2 is 2. Not 2. 1 times 2 is 2. I was about to write it again. 4 times 2 is 8, etc. I'm taking the perfect square values of over 1, up 1, doubled. Over 2, up 4, doubled. Over 1 this way, up 1, doubled over 2. Over 3, I'd go up 9 and doubled. What's 9 doubled? 18. Now, I can't fit that on the graph, but that's what the other point would be. Yes, I did all that stuff with the table, or with the mindset of substituting those in for x, but I'll be even faster with it. Anyway, so they graph it. Instead of 1, 1, they have 1, 2. Instead of 2, 4, they have 2, 8. They say compare it to it. So both graphs open up and have the same vertex and the same axis of symmetry. I'm not going to say that over and over. If they have the same thing, I'm just going to keep it the same. We already know what the parent graph does. The graph of G is narrower. I don't like that they say that. I prefer vertical stretch, but I know what they mean. Narrower than the graph of F because it's a vertical stretch by a factor of 2. So all I'd say in comparison, vertically stretched by a factor of 2. All right, let's move on forward. Let's look at another one. Compare negative 1/3 x squared to this one here. So you're going to see that they picked out some different values. And you might ask, well, how do they determine which values to pick? Exactly. If I picked 1 for x, then I'd get 1 squared, which is 1, times negative 1/3 is negative 1/3. How do I know which ones to pick and which ones not to? You'd have to have foresight or not write them down of which ones will give you fractions and which ones won't. Now, I guess I technically would need to do the same thing, but I know my numbers already. 1, 4, 9, 16, 25, 36. These are perfect squares. Which ones can you divide by 3? This one and this one. So I want to go over 3 and I want to go over 6 from 0. I don't want to go over 1 and 4 and divide those numbers by 3. Those are fine. And they did the same thing. You do it in both directions. So why do we divide them by 3? Because we're multiplying by negative 1/3. We'll talk about the negative next. It just goes down instead of up. But notice when you go over 3, that is negative 1/3 times 3 squared. 3 squared is 9. Boom. Divided or times negative 1/3 is negative 3. So what you're going to see me do is more so this. When I go over 3, instead of going up 9, well, first of all, instead of going up, we're going to go down. These graphs are negative. We're going to reflect this over the x-axis, one of our descriptions. So instead of going up, I'm going to be going down. Instead of going down 9, I'm going to be going down 1/3 of 9. I'm going to be going down 3. Boom, plot a point. I can go over 6. Instead of going down 36, I'm going to go down 1/3 of 36, which is 12. Boom, I'm going to plot a point. So without using the actual table, I'm going to go ahead and get those points, boom, from that. And that's something that you either want to pick up from me or use a table. If you use a table, keep in mind your order of operations. Now, what's different with this thing? There is reflection over the x-axis, and there is a vertical compression by a factor of 1/3. Let's see how they said it. Same vertex, same axis of symmetry, great. Opens down is wider, or vertically compressed. They said vertical shrink by a factor of 1/3 and a reflection in the x-axis. So those are the two things I'd say. Vertical compression by 1/3, reflection over x-axis. Okay, and they have other ones for us to graph. We're going to do all those together. Hopefully this is the last example, solving a real-life problem. They have, and parabolas, they exist all over the world for a lot of different things. Sound, light, a lot of different things. So I'm going to be, I'm going to like these problems. The gateway arch. I think we had a question with that before too. The diagram at the left shows the cross-section of a satellite dish where x and y are measured in meters. I guess satellite dishes need them too. It's something about the reflection pieces, the way that they can work off of the actual curve. Find the width and depth of the dish. Okay, so based off this, they have a y equals 1/4 x squared that give you some of the ordered pairs to look at here. They want you to say how wide is it and how deep is it. So we're really just looking at the graph to work off of that thing here. It's just how far does it go from -2 to 2, and that distance is 4. So that's, they talk about a subtraction probably, but that distance is 4 meters there. And really, here's the thing. This is symmetrical. This is 2 right here, and this is 2 right here. Maybe that's what they're really hitting at, that they're the same distance away from the axis of symmetry. Use the domain, the lowest. And now from here, it goes from 0 to 1, so that height is 1 as well. Are these in meters? Meters. Satellite dish is 4 meters wide, 1 meter deep. So anyway, I don't really know what else they wanted to say on that. We'll see what other kinds of word problems they give us, but at least satellite dishes, have parabolic means, or at least they estimate to that. Okay, guys, I'm going to go ahead and jump into some of these problems here. We're going to start with the vocabulary and core concept check, and then we're going to hit the core of 3 through 31. I know I spent a long time on the note lecture things to begin with, but hopefully you learned something off of it, especially how I'm going to go about doing the problems. What is the U-shaped graph of a quadratic function called? It's called a parabola. When does the graph of the quadratic function open up versus open down? It opens up when your a value is greater than 0, and it opens downward when your a value is less than 0. Basically, if a is positive versus negative, and that's the way to describe it. Remember, a cannot be 0. If it's 0, it's not a parabola, because a multiplies with x squared. I think that's the fastest I've ever done on numbers 1 and 2 for a problem set like that. So without further ado, I'm going to jump into problems 3 through 31. Check the description section down below to find what specific timestamp you're looking for. And if you need your own graph paper, I'll also attach PDFs of those ones if we are to graph, which I imagine that we are here. I'm not going to copy down problems that are graphs. So we're going to have to refer to those, and I might have to point to them out of the book itself. So I hope that you're good with that. So let's go ahead and move forward, and let's look at starting with number 3. Number 3, we are going to, in exercises 3 and 4, identify the characteristics of the quadratic function and its graph. So these aren't specifically just ax squared. This could be any form of whatever. We don't know what the equation is, and frankly, we don't care. What we are doing, though, is we are looking at the features of it, and we will describe them. So I'm going to go ahead and draw on this thing a little bit. I have a vertex right here. That vertex is at 1, -1. And that also helps me identify, that also helps me identify what the, maximum value is. This thing maximizes at y equals -1 when the x value is +1, and that's the axis of symmetry. So we have an axis of symmetry at x equals 1. That's the equation of the line. You do have to put x equals. You can't not. It is a line, and we're describing it. We have an increase on this side of on 1, and we have a decrease on this side of 1. So that stuff helps me identify what we have when it comes to the graph. And of course, like I said, we maximize at -1 for y, so that helps me with my range. So what are the features we can talk about? Well, I just listed some of them. The vertex is at 1, -1. The axis of symmetry is at x equals 1. It's going to be the same as the vertex x value. That's kind of nice to know. The domain is going to be all real numbers. The range is going to be y is less than or equal to -1. Since it opens downward, it's going to be from the vertex y value and downward. Domain should just be all real numbers for here. It's increasing on the interval when x is less than 1. When x is less than 1, we see an increase on y. That means everything from the left side of 1 all the way up to 1, it's increasing. And it's decreasing when x is greater than -1. Is there anything else? I think that's all we're going to kind of put there. So that's my list. All right, I'll just list it like that. Number 4. Now this time I will write it all here, although I will do the drawings on this here. So number 4. Let's locate its new vertex right there. I'm going to draw its axis of symmetry, and I'll draw arrows for increase and decrease. Outside of that, I'm going to go ahead and write them on this other page. So decrease here and increase there. Okay, so number 4. We do have a vertex at, look at the scaling, it goes by 2s. So at -2, 4 is the vertex itself. We have an axis of symmetry at x equals -2. It's that vertical line. This thing has a domain of all real numbers, as they all shall. It has a range of y is greater than or equal to 4, because it opens upward, and 4 is the minimum value. This increases on the interval when x is greater than, notice the increase is to the right this time, when x is greater than -2, and the y values decrease when x is less than -2. So that is our description of the behavior on 3 and 4. Nothing to graph, no equations to write, definitely nothing to solve, and that ends up being it. All right, we have 5 through 12, where we are going to be doing some graphs. So, they ask us to use a graphing calculator next. I did not anticipate that. We'll see what we do from there. Well, I can use mine. That's okay. But I don't imagine you guys all necessarily have one, unless you use Desmos. But numbers 5 through 12, graph the function. Compare the graph to f of x equals x squared. Keep in mind, before I do this on these other ones, for f of x equals x squared, I am not going to mention things that don't transform. So for f of x equals x squared, the vertex is at 0, 0. It opens up, and axis of symmetry is at x equals 0. Well, all these are still going to be there. So listen, these things aren't going to change because this is f of x equals ax squared. But vertex is at 0, 0, and it opens up and all that, right? So from here, we're just going to see what happens when it doesn't open up and if there's a vertical stretch or compression compared to what it would normally be. But I am going to graph these. And in graphing these, I need to do this. I need to copy, paste. There we go. I'm going to shrink that a little bit. Okay. I'm going to copy down the problem, and we'll talk about how I'm getting this done. Without use of a table, 6x squared. Without use of a table, let's have the knowledge of x squared graphs and what they do. First of all these vertexes will be at the origin. I don't need to talk about translations with you guys yet. Not in this section. We'll talk about them later. But everything I do, I'm going to let you know now, everything I do is with respect to the vertex that I draw. meaning it'll be my new origin regardless, but it's at the origin this time. Normally we would go 1, 1, 2, 4, 3, 9, 4, 16 on both sides of this graph. The reason being is because 1 squared is 1, 2 squared is 4, negative 1 squared is 1, negative 2 squared is 4, negative 3 squared is 9, like that. But we're about to multiply our numbers by 6. So instead of 1, 1, we're going to have 1, 6. This will be vertically stretched. Negative 1, 1, nope, negative 1, 6. X doesn't change. I'm still plugging in 1, negative 1 for this to happen. Now, I can't fit any other points other than this. This is a great introduction problem to show you on how vertically stretched this thing is. Because instead of 2, 4, what's 4 times 6? Well, that's 24. So I would have had a point that's 2, 24. And that's quite the height here. Nothing I can fit on this or even a taller graph. I'm sure they'd force you to change scale. And I'm not going to do that. So here's this set of values. And yeah, we just work off that, and that is, that's that. So let's describe it. This thing is a vertical stretch by a factor of 6. It doesn't flip over, it didn't translate, but that's how it compares to f of x. Vertically stretch f of x by a factor of 6. Excuse me, this was g of x equals. I was going to say, it's not our f of x. So that is number 5. Number 6, let me make sure I can copy and paste this graph each time. Number 6, we have b of x equals, 2.5x squared. So they might be forcing me into table-ish stuff, which is no fair. That's not what I wanted to do. And listen, life isn't fair as far as, hey, I give you a graph, you got to graph it. Now, I can still work off of it. I just need you to hear me out loud in what I say. So the origin is 0, 0. Excuse me, the vertex is at the origin 0, 0. Still a vertical stretch. You make everything 2.5 times larger. 1 times 2.5, 4 times 2.5, 9 times 2.5, 16 times 2.5. All those. That's all you're doing. 1 times 2.5 is 2.5. 4 times 2.5 is actually 10, so that's a good one. When I go over 2, I'm going to go up to 10. And by the way, I should have done this on the other graph. Mention the axis of symmetry. This guy right here. These all have an axis of symmetry on the y-axis. I'm not going to do this each time, but I do want to show it here because there are faster ways to plot graphs, quadratics, on both sides of this thing, just by recognizing, instead of going over 1 and counting up 2.5, if that makes sense, this should be the same distance away at this height. So I just have to go 1 over from here and 2 over from there, and that'll get me my other points of my graph. Now, I don't need to draw this axis of symmetry each time, one, because it's on the y-axis. I gotta sneeze. 1, because it's on the y-axis, so you already have it drawn. And 2, they're not asking you to. We're not, this thing's not translating at all. I just feel like it's not a necessary component to have for these things. But this is going to be the same kind of thing as number 5, which is, it's a vertical stretch on this number 6 here. So same thing, vertically stretch f of x by a factor of 2.5. I imagine we'll have some shrinks and reflections as well. They're going to pop up. That's number 6. Okay, number 7. Let's move this over first. Number 7, h of x equals 1/4 x squared. Now I'm fine with fractions and such because we get to mention it. And 2.5 was 5 halves. I just kept it as 2.5. So h of x equals 1/4 x squared. So this one, still vertex at the origin, of course. That's not going to change. Instead of going over 1 up 1, we're going to take a fourth of that 1 going up. So we're going to divide it by 4. 1 divided by 4 is 1/4. 1/4 of 1 is 1/4. That makes sense. Instead of going over 2 up 4, we're going to divide that by 4. 4 divided by 4 is 1. So I'm going to slow that down again. Say that one more time. 1, 1, 2, 4, 3, 9, 4, 16. Those are the standards of a quadratic graph. That's what we would generally do. But here we are not. Here we have to vertically compress them by a factor of 1/4. That's literally going to be my description on this thing. Everything's going to be 1/4 the height of what they were before. So divide 1 by 4, 4 by 4, 9 by 4, 16 by 4, all that. The x's still go over 1, 2, 3, 4, 5, 6. It's still going to be faced upward. But you take 1/4 of their heights without even writing that in a table. Now, you might not know 9 divided by 4. I'll tell you it's 2.25. If you didn't know that, maybe move on to the next value. Just take ones you can divide by 4 pretty easily. So I'll do that the rest of the way. Over 4 up 16 divided by 4. 16 divided by 4 is 4. Boom. 25 divided by 4 is not clean, so we'll save that one. How about, because that's 5 squared, 6 squared is 36, divided by 4 is 9, so how about I fit that one? Now I'm fine doing 25 divided by 4 myself, that's 6 1/4. So I can get a smoother curve. And I'm going to do the same thing on the other side. And again, if you're not a fan of counting upward those quarters, just reflect over. 1 away, 1 away. 2 away over here. 3 away. 4 away. 5 away. 6 away. You can see where that count works. And I love these vertically compressed graphs. They really show the character and the nature of these parabolas this way. That number 5 was just so stretched out. It was just kind of hard to take care of. I know you guys might not be a fan of fractions, but I love completing these in that form, making it look really, really nice. And I think that's one of them. So good, good, good. Now let's describe it. This is vertically compressed this time. They'll say vertical shrink. I'm just sticking with my own terminology. Maybe your teachers go one way or the other. They should be the same thing. Vertically compress by a factor of 1/4. As long as your number is less than 1, it'll flip over. I imagine this next one, yep, this next one will be a decimal bit. It is number 8. Okay, so hopefully you heard some of those things. Obviously, I'm calculating in my head for a bunch of these things, so I'll be speeding up over time. J of x equals 0.75 x squared. Now, 0.75 is also 3/4. I think I might ask you to imagine that for the sake of some of the numbers that we get, just so it's good. So 3/4 of 1 is 3/4 over 1 up 3/4 of 1. Over 2, instead of going up 4, we're going to go up 3/4 of 4. 3/4 of 4 is 3. Over 3, up 3/4 of 9, not one of my preferred ones. 27/4 is 7 3/4, so it's kind of a weird one. But if I can fit it, I'm going to. So 7 3/4 is kind of up there. Over 4, 3/4 of 16 is 12. I can't fit it, but I can imagine where it would be, sort of. So if that kind of helps, you can look at it like that. And that would kind of be it, what we can fit. And let's reflect those on the other side. So 3/4 of 1, 3/4 of 4, 3/4 of, excuse me, I said 7 3/4. That'd be 6 3/4 for this. I thought that looked a little weird. 3/4 of 20, hold on, what was I talking about? 3/4 of 9 and 3/4 of 16. Okay. By the way, none of these things change with the stretch factor if I do translate the vertex in future sections. This is another compression. It's less than 1. Because it's 3/4. Okay, there it is. And we're going to hit negatives for numbers 9 through 12. So let's keep going. Number 9. M of x equals negative 2x squared. Okay, let's go. So negative 2x squared. So vertex is still at the origin. And that whole vertical stretch factor thing, double our y values, is not going to change. What is going to change is instead of going up, we're going to be going down. So imagine a reflected parent function going over 1 down 1, over 2 down 4, over 3 down 9. So when I count, just follow my pencil thing. 1, 1, 2, 4, 3, 9. Now I'm going down instead of up. That's what the negative's doing. But let's double those y values. So instead of 1, 1, it's 1, 2. Instead of 2, 4, it's 2, 8. Again, you're doubling those. These will appear in your table. I mean, that's what they're going to look like in your table. So if you want to make a table, great. Reflect it across the axis of symmetry. And, you know, they didn't mention this for the table bit as well, although you probably need to practice your order of operations here or there. Things reflect across the vertex in that way. That's the whole point of the axis of symmetry. Don't compute things more than once if you don't have to. You'll get the same value on the left side as you will on the right side. That's why I just keep going over like that. So 2 things happen this time. You do reflect over the x-axis for 1. Or reflection in the x-axis, but reflect over x-axis and vertically stretch by a factor of 2. By factor, sorry about the writing, of 2. You don't say -2. That's what the reflection piece is all about. We always say that it's just a positive, just absolute value number. Number 10, q of x equals, funky fraction, -9/2 x squared. So 10, q of x. Thankfully, I probably can't really fit very many points, at least for my scale. -9/2 x squared. Once again, flipped over, so we're already aware of that part. Now, -9/2 is also -4.5, so we're multiplying every y value by 4.5 as we go downward. 1 times 4.5 is 4.5. Let's reflect that over. 4 times 4.5 is 18. That's already well beyond the scope. It's way down there, and I can't quite fit that. So this is all I can really fit. Now, the point I want to make on this graph here is if you can't fit a point, then you do not reach the next x value, meaning this. Do not draw your graph to do this. I just crossed x equals 2 right there, and I should not have. I should not have crossed x equals 2 because x equals 2 is when y is -18. I would have, if I could have plotted the point and fit the point, I would have. And I couldn't, so I didn't. So do not cross an x value that you can't hit. Otherwise, hit it. It's a small thing, but a big thing. All right, reflect over x-axis. And it is more than 1. Vertically stretch by a factor of 9/2. Remember, 9/2 is 4.5. Number 11, going with the interesting fractions still, or decimals. K of x equals -0.2 x squared. Okay, so we have reflection over the x-axis. Now, 1 times 0.2 is 0.2. That's 1/5 of the way down, less than a quarter. 0.2 times 4. 4 times, now remember, instead of going down 4 times 0.2, or 1/5 of that. 1/5 of 4 is 4/5. That's one way of saying it. Or 4 times 0.2 is 0.8. We're still less than 1 on this guy right here. We're 1/5 away from -1 on that guy. So this is going to be quite shrunk. I'll fit what I can, though, right? 9 times 0.2 is 1.8. So I'm going to be down here at -1.8 like that. 16 times 0.2 is 3.2. So I'm actually doing the calculations. I'm just not, I've already squared the numbers in my head, though. Right? That's kind of the point. I'm squaring the numbers in my head instead of writing out what that is and doing it in a table. Because I know I'm just going to reflect them across anyway. 25 times 0.2 is 5. 1/5 of 25. So that one fits quite well like that. 36 times 0.2 is 7.2. 6, 7, -7.2 like that. And 49 times 0.2 is -9.8. So, hey, there are a lot of points I can fit and going on the other side. I can't imagine which ones. I bet they'd only fit 5 and 10, and they'd scale it by 10s, because 100, 10 squared is 100. 100 times 0.2 is 20, and I'd have to fit -20 down there. But I'm fitting what I can within my own scale, and again, if you borrow my graph stuff, PDFs and such. I mean, the book didn't provide you anything. Notice what I'm doing here. I'm reflecting across equal height on this side without even remembering what the numbers are. I just need to line them up. I just need to make sure that they are equidistant and it follows the axis of symmetry. And this thing does curve. It does sharpen more over time. You can kind of tell by my tracing. Obviously it does early on. That's not straight right here. This is sharpening. And there it is. This is reflected over the x-axis once again. Reflect over x-axis. And vertically compress. Totally. Vertically compress by a factor of 0.2. Whew, number 12. See, these things go a little slowly with graphs. It takes time. Factoring could have gone really fast, and that's not what this is anymore. Number 12. P of x equals -2/3 x squared. Okay. Vertex at the origin. We're going downward, and we're going to go 2/3 of 1, 2/3 of 4. This time, outside of 1, I'm only going to go 2/3 of clean numbers. So 2/3 of 1 is 2/3. Same thing on the other side. 2/3 of 4 is not clean. 2/3 of 9 is clean. 2/3 of 9 is 6. So instead of going over 2 in down amount, let's go over 3. Instead of down 9, we're going down 6. That's 2/3 of 9. 2/3 of 16, nah. 2/3 of 25, nah. 2/3 of 36 is 24. That's way too far out. So, you know, these are the only valid points I'd hit. If I did want to hit some more, I could kind of like plot them here and here, stuff like that. And yeah, anyway. So I'll do what I can. Yeah, 2/3 of 4 is 8/3. So that's where we would have hit next with that, by the way. So reasonable enough, I'd say, for that. Reflect over the x-axis. One more time. And is a vertical compression since it's less than 1. Vertically compress by a factor of 2/3. Okay, those are some early graphs there. Let's move forward. Oh yeah, graphing calculator. Use a graphing calculator to graph the function. Compare it to negative 4x squared. Yeah. Here, let me pop up my graphing calculator and kind of see what I want to say about it. I could tell you what some of the things are going to be from it. So, now 4x squared, negative 4x squared is already flipped over. It's vertically stretched by a factor of negative 4. So let's pop up the graphing calculator here, and I'm going to get f of x equals negative 4x squared. Let's just look at what this looks like here. I'm going to do something from an old school thing. Negative 9.4, 9.4. I remember this from way back in the day. Just ignore what I'm doing. If you're curious, I'll tell you a different day. Anyway, so here's that graph on that thing, negative 4x squared, right? Let's do the different one. Let's look at different ones with different designs. I'll make this one bold, and let's do 4x squared. So how is this one going to compare? Well, it's going to be an upward version of it. So it's going to look like that. There's 4x squared. This is number 13. So for number 13, when you have that appearance, do they say use it to graph the function. So I guess I got to draw these graphs now. I mean, I'm fine with this one. It's the negative 0.04 and 0.004 that I'm curious on how I want to go ahead and do that. But just go ahead and take a look at that graph and see what the difference is. Again, the parent function was negative 4x squared. But y equals 4x squared. Let's do this. I'm trying to think how to show you these at the same time and stuff, because I can't show you both things at the same time. Okay, let me go back. So I wrote this so far, and I'm going to make this blue, right? Negative 4x squared, the original one, is going to look like this. It's going down in times 4. 4 times 4 is 16, so I can't fit when x equals 2, so it's just going to go sharply. Boom, boom. Whoops. I'm trying. All right, now let's do the one in blue. The one in blue is just an upward version of that. So 4, vertex at the origin like that. And same concept here. Okay, and that is a V shape. Don't get me wrong. All right, so there's the first one. Number 14. And they ask you to compare it. Before I hit number 14. Reflect over x-axis. Okay. Number 14. Y equals negative 0.4x squared. So what's different between negative 4x squared and negative 0.4x squared? Negative 0.4 is 10 times less than negative 4. So this is going to look something, it's going to be 10 times less and take on that appearance. Well, let's see what the graphing calculator says about it, because they ask us to. And of course, I could use those. I could, compute what's 1 times 0.4 and things like that. I probably will for some of them. So let's go back to the graphing calculator, see what that thing talks about, graphing calc. And let's get negative 0.4x squared. Okay. So compared to the original, this is going to look like that. It's more vertically compressed. It is 10 times vertically compressed, as in at some x value, the y value is 10 times smaller, right? So instead of, let me go back. normally we'd go 1, 1, 2, 4, 3, 9, 4, 16, things like that. And we're not dividing those by 10, but we're dividing 1, 4 by 10. 0.4 times 1 is 0.4. So 0.4 here and here. 0.4 times 4 is 1.6. 0.4 times 9 is 3.6. So we're literally just getting, I use the graphing calculator, great, but now I'm actually just graphing it. So it's no difference. 16 times 0.4 is 6.4. They did say use a graphing calculator, so whatever. 25 times 0.4 is 10. Cool. So it's going to look like that instead of the one that you see in black. Now, compared to the black, it is not reflected over the x-axis. They were reflected to begin with. This thing is 10 times smaller, though, than the black. So this is a vertical compression. This is vertically compressed by a factor. It's 10 times smaller, so I want to say 1/10. Factor of 1/10, like that. 10 times smaller. Okay, the next one's 0.04 and then 0.004. So I imagine once I hit the 0.004, you're really not going to see the nature of the curve, and I don't really know what I can put for you guys when it comes to scale. We'll just go ahead and see what it looks like then. But let's pop up this next one. Let's go to graphing calculator, and let's look at when it's negative 0.04. So this time it's going to be 100 times smaller or shrunk than the other thing. So here's the original. Let's look how wide that goes. Pretty wide. It still has some character, though, that we can see. So I'm going to go ahead and start to get that one drawn, graphed out. Number 15, y equals negative 0.04x squared. All right, let's go and take a look at this. So negative 0.04x squared. You see that curve, or you saw the curve in comparison. This is where I can take these things and divide them by 10, I guess. So 0.4 divided by 10 is 0.04. I think it's kind of easier to do this now that I see the points. I wish I remembered them. 1.6 divided by 10. 1.6 divided by 10 is 0.16, kind of like 0.2. 3.6 divided by 10 is 0.36, so about a third. 6.4 divided by 10 is 0.64, a little less than a half, or more than a half, I should say. And 10 divided by 10 is 1, so negative 1 there, and you can kind of see that stretch, and like I said, or compression. It does that. How about now 10? 10 squared is 100 times 0.04 is negative 4. So I know we're going to hit this eventually as well. And that's really the extent to which I'm going to do this stuff. Because this is kind of an overkill of what they're asking me to do. They said to graph the function. I'm graphing it. And it does curve. You can tell that it has a bank, but it's so much wide. It's probably too wide for its own good. I talked about good character. The green one has good character. There were weird points, but that goes pretty far there. That's a vertical compression by a factor of 1 over 100. Vertically compress. It's 100 times smaller than the original. By factor of 1 over 100. Still flipped over. And the last one, number 16, let's see if this even shows up on the graphing calculator with my own scale. Obviously, I could change the scale, but I'm just working off what we have. So on this one, we're going to do negative 0.004. Okay. At least you see something, right? But here's the one thing. So I'm not going to fit any good looking points. Remember, this is 10 times smaller than the one I just did in purple. So what's the difference on this one is, what color? I guess red. Y equals negative 0.004x squared. This one now, what's 10 times smaller than 4? 0.4. So now this 0.4 shows up when x is 10 and negative 10. It's way far out there, and that's really the best I can do when it comes to fitting good points. You're barely even going to see the curve in action. It's just going to kind of approach that and shoot out. It's a parabola, but it ain't one that's very noticeable for its characteristics, and it's going to look like that. So I can kind of graph it. It's like that. But the description, compared to the original black, that's 1,000 times smaller on Y. Vertically compress by factor of 1 over 1,000. And that's what's going on there. That's how 0.004 compares to 4. Or negative 0.004 compares to negative 0.4. Okay, so that's up to number 16. We're only halfway through, so I hope that these kind of speed up a little more over time. Okay, number 17, error analysis. How long have we gone so far? 50 minutes. Error analysis. Describe and correct the error in graphing and comparing x squared and 0.5x squared. So I'm looking at 0.5x squared in blue, and it looks vertically stretched instead of compressed. That looks wrong. What they might have done is they might have made the graph half the width at the same heights, which is one reason I don't want to mention narrower. First of all, these graphs are not narrower or wider. The domain's all real numbers. I guess the range is not limited either on one end. But secondly, it's because we're not changing x, we're changing y. So maybe that's what they did. So let's see what they said. The graphs have the same vertex, same axis of symmetry. All that's good. It's narrower than the graph of y equals x squared. So their description, they don't even talk about the vertical stretch or compression or horizontal. But I would just assume that what they did when they said narrower is they took the 0.5 and said let's make it half the width. So they took half the width instead of half the height. That's my guess on this. That's what it looks like. The height. The graph should be vertically compressed. Therefore, let's see, and not horizontally compressed. So when you fix it, I would say vertically compress by a factor of 0.5. I'm not going to go much more than that. The rest is good. Well, their graph's not good, right? Their graph should have went, and listen, they don't have a scale, and I'm not going to draw this whole thing again with a scale. Actually, maybe I can. Maybe I should. Let's do that, because we haven't done a 1/2 yet. Okay, so for this one here, if you have your, because I want to compare these things, right? Normally we do 1, 1, 2, 4, 3, 9, and we reflect across here. Here's your standard y equals x squared parent function graph. Something you want to know: 1, 1, 2, 4, 3, 9, 4, 16, all those kinds of things. You want to know your perfect squares for that. So there's that. Boom, boom. Okay. Now we're going to take this new one. It's going to be vertically compressed by a factor of 1/2. Instead of 1, 1, half of 1 is 1/2. Instead of 2, 4, half of 4 is 2. Instead of 3, 9, half of 9 is 4.5. Instead of 4, 16, which I couldn't fit on black, half of 16 is 8. So remember, both these graphs do go forever, left and right. This one I might be able to fit more y values for those x values that we're talking about, but they still do kind of have that. So that might be why someone describes this as wider, because all you see is just for these particular heights. So we just say, oh, look, it's wider. Sure. But it's shorter for those x values. That's what matters. And there's the graph in comparison. So like I said, they may have doubled the heights or halved the widths. All right, number 18. The arch support of a bridge can be modeled by y equals negative 0.0012x squared, where x and y are measured in feet. Find the height and width of the arch. So listen, they gave you an equation. We're not going to use really much of anything off of it unless you wanted to plug in values. But it looks like by scale, we're hitting these exact values here, and we can kind of know that the origin's right there. So they're saying find the width, find the height. Let's kind of do it just based off what you see on the thing itself. The width goes from here to here based on axis of symmetry. These go by 50s, so 50 to 450, 500. So this distance here is 500, and this distance here is 500. You add those together, and you will get 1,000. That will be the width. I'll write that down in a second. This height, as these also seem to go by 50s, looks like 300 feet in height. So just based off those measurements alone, taking a look, I wonder really what they want to do with these things outside of understanding axis of symmetry. Number 18, the width is 500 plus 500, or 500 times 2, which is 1,000 feet. The height is 300 feet. And that is of the arch. And that's it. Much faster than some of the other ones. Number 19, multiple parts. The braking strength Z. in pounds of a manila rope can be modeled by the breaking strength. What am I looking at there? Can be modeled by Z equals 8,900 D squared, where D is the diameter in inches of the rope. Oh, I see. So they're showing a zoomed in threshold. I thought that was part of the thing. So they're showing a zoomed in threshold of the rope, and that's how big the rope coil is, the D right there. Describe the domain and range of the function. So for number 19, we have Z equals 8,900, D squared. So let's describe the domain and range of the function. I just came off saying domain is all real numbers always, but you have to imagine that we do need a rope. So that rope needs a diameter. It means the diameter can't be negative, and it also can't be 0. So for this particular problem on part A, the domain is going to be D is greater than 0. That only makes sense for the context of the word problem. And word problems will have context things like that, just like this arch. This arch's domain isn't all real numbers because the arch doesn't go forever. It goes from negative 500 to positive 500. And that's just it. So it's limited on that. Now the range can be limited based on domain, and this one's partially limited based on domain, because normally this graph would have gone like that. Obviously it's going to be very vertically stretched, but now we won't have a negative part of this, and guess what? We also won't be at the origin anymore either. So now the range is limited based on the domain. The range is Z being also greater than 0. Only positive numbers can come out from here when it comes to breaking strength in pounds. So Z has to be some number of pounds. It looks like it'd be greater than 0 based on that for A. Part B, graph the function. Well, I kind of did. So there you go. And there's a point that's 1, 8,900. How about that? Boom. That's part B. C graph. Sorry about that, but that's just going to make the most sense with regard to what I do. Open circle at the origin, nothing graph to the left, and make it a parabola. Make it much better looking than I just did. Part C. A manila rope has 4 times the breaking strength of another manila rope. Does the stronger rope have 4 times the diameter? Explain. Well, I'm going to tell you no. And the reason is in that quadratic nature. If something's 4 times the height in y on a parabola, that doesn't necessarily mean it's 4 times farther on x. In fact, that would be a false thing to think about. We know 1, 1, 2, 4, 3, 9, 4, 16. The y's separate themselves a lot farther out as x just goes over by 1. So no, that's not the case. So no, well, let me type this. No, because the behavior of a quadratic function, such as this, dictates that the separating distance dictates that as every shoot. I just said it before, and I have to find a way to say it again. Dictates that the separation in pounds, no, in inches? In inches of the rope's diameter is not the same as the separation in pounds of the breaking strength of the rope. That's not the best thing I want to say with it, but that's that. Basically, it would probably be half that amount for inches, meaning it's probably half. If you have, let's see, how did I say it? A manila rope has 4 times the breaking strength. The diameter is probably twice as large because of quadratic behavior. If a manila rope has 4 times the breaking strength of another manila rope, the stronger rope likely has only twice the diameter. Again, 2 squared is 4. That's why. Double the diameter, quadruple the rope strength, the breaking point. Okay. Now, I don't know if you have to mention all that, but I'm mentioning it for you so you can learn it. All right, number 20. How do you see it? Describe the possible values of A. I'm not going to draw these again. So for part A, for blue, for g of x equals ax squared, the a values are something probably greater than 1. You can see where it says y equals x squared. And that means 1x squared. Because it's a vertical stretch, it's likely that it's greater than 1 is the nature of that. For part B, we have the same thing, g of x equals ax squared, but this time it's flipped over. And it's not just flipped over. So it's not just negative. It's not just a is less than 0. But it also looks vertically compressed. That means your value needs to be somewhere between 0 and negative 1. Because if it was negative 1, it would have the same vertical stretch amount. If it was less than negative 1, like negative 2, negative 3, negative 4, negative 5, it would be more vertically stretched. So it needs to be somewhere between 0 and negative 1 for part B. Okay, that was a good fast one. Number 21 to 25. Use the graph. 21 to 23, use the graph, excuse me. When is each function increasing for f of x and g of x? There's increase on f of x here and increase on g of x here. There are different intervals for which we have the increase amount for both of these guys. So f of x increases when x is greater than 0. To the right of the origin, it does. Now, to the left of the origin, g of x increases. G of x increases when x is less than 0. You don't want to say as we go to the left. You want to say coming from the left side, you see it increase, right? Coming from the left side. From numbers left of 0 is where you see it. Up until 0, you see it increase. Number 22, when is each function decreasing? That's where we see f of x decreases left of 0, right there, left of the origin on x. G of x decreases right of 0. So it's going to be the opposite. There, decrease, decrease. I haven't looked at 23, but it's probably when are they the same? When are they neither increasing nor decreasing? We'll see. F of x decreases when x is less than 0, and g of x decreases when x is greater than 0. All right, fateful number 23. Which function, different question. Which function could include the point negative 2, 3? Find the value of a when the graph passes through the point negative 2, 3. So negative 2, 3 would have been up here. If that would have been an f of x equation because the a values are greater than 0 there. So f of x could include negative 2, 3. Now they ask you to find the value of a in that case. Now here's where you can do this. There are a couple ways. Like I know the answer is going to be 3/4. The a value is going to be 3/4. But here's what you can do. We have an equation that says f of x equals ax squared, right? F of x equals ax squared. They said find the value of a when this x gives me this y. So let's substitute 3 for y, negative 2 for x, and then let's solve for a in that scenario. Because that's going to be a solution to this particular equation, and this a will give us that. When we divide both sides by 4, we get 3/4. So that's the answer for a. They said find the value, so that's it. So that therefore you would have an equation that's f of x equals 3/4 x squared. That's an equation that would give you negative 2, 3, basically. Okay, number 24, unrelated to those it looks like. Is the x-intercept of the graph of y equals ax squared always 0? Justify your answer. So this is where students kind of have trouble with intercepts and understanding what they are. It's not just where they pass axes. I mean, it is. It's absolutely where they pass axes. But algebraically, how can we look at that? Is it always 0? An x-intercept is the value of x when y equals 0. So let's set, if we have y equals ax squared, for the x-intercept, let's set y equal to 0. 0 equals ax squared. And let's solve. It says, what are the x-intercepts? I divide both sides by a, because a does not matter in this case. And you get 0 equals x squared. And I take the square root of both sides, and you still get x equals 0. Are they asking, is the x-intercept always 0 in this case? Yes. They said justify your answer. I just did. There are other ways I could talk about it. We've already seen our parabolas here. It either goes up or down. There's no transformation on translations. Now, this is ax squared, not ax squared plus bx plus c or something like that. This is without translations. Yes, that'll be its intercept forever and always. This is with a domain of all real numbers, unlike that rope diameter question. So, yes. Number 25, a parabola opens up and passes through negative 4, 2 and 6, negative 3. How do you know that negative 4, 2 is not the vertex? All right, well, let's look at what that looks like so we can kind of describe that best. So negative 4, 2 would be like right here. 6, negative 3 would be like right here. And they said the parabola opens up. If negative 4, 2 was the vertex, then there would be no values below 2. 6, negative 3 is not possible. Now listen, there's a parabola that can go through here. I could hit a parabola that goes like, I could hit a parabola that does that. And if it does, that could be the vertex. But if the parabola opens upward, it's not going to hit 6, it'll hit 6, something, but it'll never hit negative 3 for y. So let's explain that. Let's say if a parabola opens upward with negative 4, 2 as its vertex, then it will never hit a y value of negative 3. This is because the range is y is greater than or equal to 2. Let me find that symbol. Greater than or equal to 2. There. That ought to do it. All right. Almost done. Number 26. 26 to 29. Determine whether the statement is always, sometimes, or never true. Explain your reasoning. Now, I mentioned for always, sometimes, and nevers. Don't assume, if you don't know, don't assume the answer is sometimes. Sometimes is actually the case when you know for sure a case that it does work, and you know for sure a case that it doesn't work. So we'll see if we hit sometimes. The graph of f of x equals ax squared is narrower than the graph of g of x equals x squared when a is greater than 0. So, I mean, I think I know the answer, but I just want to compute that because narrower also means taller. So I'm just going to say taller, more vertically stretched, just so we're aware of what we're talking about. Taller as far as vertical stretch. So when a is greater than 0, is it always taller? No, not necessarily. Sometimes it is. This is a sometimes, so this is where we're going to justify this. Sometimes, if a is greater than 1, it will be taller, narrower. If a is less than 1, between 0 and 1, it will be wider, because it will be vertically compressed. So keep that in mind. Whoops. They just said if it's positive, right? These are two different positive sets. That's an example of sometimes. All right, number 27. The graph of f of x equals ax squared is narrower than the graph of that when absolute value of a is greater than 1. This one's actually always true. So with this one here, you can't prove by example necessarily, but let's support what they're talking about. When they say the absolute value of a, they want to make sure that they cover all bases and say, what about when a is negative 3? See, it's flipped over. That doesn't mean it's not more vertically stretched, that it's narrower, because it is. That's why whenever I say you go down, but it's still a vertical stretch by a factor of whatever, because it's a larger negative, it still counts. So negative 3 may not be greater than 1, but the absolute value of negative 3 is. Whereas if it also equaled, if a was negative 1, absolute value of that is 1, and that's not more vertically stretched, and that's not what we're looking at. But so always, whether largely positive or negative, narrower equals vertically stretched, and absolute value of a greater than 1 will satisfy that. I don't know if that's my best way of supporting that answer, but that's what I explained to you is kind of going to work that thing out. All right, number 28. The graph of A is wider than the graph of this when A is between 0 and 1. Excuse me, the absolute value of A. Once again, always true in this case. It's just going to be the opposite effect of what you saw from the last thing. It's going to be vertically compressed, whether positive or negative. You are looking at a fraction less than 1 on either side, flipped up or down, and it's going to be more vertically compressed. Whether a small fraction less than 1 value, when I say less than 1, I mean that between negative 1 and 1. Hopefully that makes sense. Whether a small value is negative or positive, a wider graph is vertically compressed. And 0 is less than A, less than 1 will satisfy that. So again, I'm not sure if I'm mentioning that best, but I am getting the right answer. See, justifying something really is like in a proof, and with proofs you can't prove by example. The sometimes cases I can. So I can just say an example when it does and does not work. Number 29, the graph of f of x equals ax squared is wider than the graph of g of x equals dx squared when the absolute value of a is greater than the absolute value of d. Sounds like they have that case backwards. So their support things, I don't think they need us to support everything under the sun with regard to this. I think they just want us to know how absolute values work and the words wider versus narrower. Honestly, I think that's all that they're talking about. In this case, this is never. When a is greater than d, the graph will be, absolute value of a, the graph will be more vertically stretched, which makes it narrower. So this is never. When absolute value of a is greater than absolute value of d, the former will be more vertically stretched and therefore narrower, not wider. Now remember, that's on the negative or positive realm, right? Absolute value of negative 10 is greater than the absolute value of negative 2, and then it will be taller. Okay. 2 more questions. Here we go. Number 30. Draw the Draw the isosceles triangle shown. No. Yeah, I guess I have to. Divide each leg into 8 congruent segments. Okay. I thought those were graph axes. Connect the highest point of one leg with the lowest point of the other leg. Then connect the second highest point of one leg. I gotcha. To the second lowest point of the other leg. Continuous process. Write a quadratic function. Oh, cool. So, okay. All right, check this out. So, yeah, let's, can I copy and paste their thing over? Because I'm not going to do mine to scale well. I don't know how to draw. Actually, hold on. I can draw it here. I can, I'm gonna use theirs. I get to cheat a little bit. It's going to be tough for you guys to be able to do it, though. But I want to make sure I have one perfectly to scale. I don't really want to mess this thing up. Hey, look at that. So they started off the process. I wonder who made up this problem. It's an interesting problem. Okay. So this is number 30. Okay, so you connect points as follows. They already started a set. So this point here connects the point when it lowers. This point is going to connect to this one now. And this point connects to this one. And this point connects to this one. And this point connects to this one as it lowers itself down. And this point connects to that one. And they already did that one. I'm going to kind of just fill them all in together. And you get that kind of neat O appearance. Like that. And it kind of forms like this parabola thing. That's kind of neat. Now, what are they asking us here specifically to do? You have a point that's 0, 4 right here. And you have 6, negative 4 down there. So we have to imagine what this whole scale is. That means that this point must be 0, negative 4. And this is 1, 2, 3, 4, 5, 6, 7, 8. This is exactly halfway in between. So this specific, let's see, what do they want here? Write a quadratic function whose graph models the shape that appears. So we kind of want to draw a graph, I guess, that just does that, right? I don't know specifically. I think they want us to draw that, state what that quadratic is. So if that's 0, -4, then this point right here would be right in the middle because that is halfway through. So that point is 0, 0. What they want you to do is make the quadratic equation that hits, I guess, there and there, I guess. I don't really know. Maybe, maybe not. But if so, we can, because this is all about ax squared. I think it would make sense if we spoke on it that way. So we do know that it's going to be a y equals ax squared equation. Now here we have a point like 6, -4. That's an xy, or -6, -4. Let's do the same things we did on that one problem where we found 3/4 as that a value. We substitute -4 for y. We substitute 6 for x, and we find out if you go 6 over and just 4 down, what's it going to be? Now I'll tell you what it's going to be. It's going to be -1/9. And the reason is because normally we'd go over 6 and up 36, because 6 squared is 36. But instead we're going down. So instead of down 36, we're going down 4. What is 4 compared to 36? 4 is 1/9 of 36. So how's this going to be? -4 equals 6 squared, 36 times a. Divide both sides by 36. You get -4 over 36, which is -1/9. So this will be the equation. Y equals -1/9 x squared. And that's what I think that answer is supposed to be. I can imagine that's what it is based on what they're doing. Hopefully that's right. Hopefully that makes sense in terms of what it's doing. That's just okay. All right. And last question, number 31. Making an argument. The diagram shows the parabolic cross-section of a swirling... Oh, yeah. I kind of have... Oh, I'm out of water. Of a swirling glass. I don't really know if I'm getting the parabola thing. I can't do it. Of a swirling glass of water where x and y are measured in centimeters. About how wide is the mouth of the glass? And your friend claims the rotational speed of water would have to increase for the cross-section to be modeled by this. Is your friend correct? Explain the reasoning. All right, let's start with A. I don't know what B's answer is just yet. I haven't really looked at it. So let's start with A. They just say about how wide is the mouth of the glass, just that width and diameter there. It goes from -4 to 4. Make sure you read your x's, not your y's. So that distance of 4 and that distance of 4. The width is 4 plus 4, which is 8. Width is 4 plus 4, which is 8. Centimeters? All right, that was an easy part. B, your friend claims that the rotational speed of the water would have to increase for the cross-section to be modeled by 0.1 x squared. Is your friend correct? Explain your reasoning. So the real question is, at still, mine obviously isn't perfect. Mine isn't even swirling right? But at still water here, it's flat. So I imagine that the more you rotate it, now again, mine's not going to do it quite. Well, I guess it still does. The more you rotate it, the more of that swirl effect you'll get. So it means the taller the swirl will be. So if I increase rotational speed, I'm going to then see something that would be, if I increase rotational speed, then it would do more of this, right? Clearly not that much. It's not a centrifuge or whatever. But I'm just saying the more you increase speed, the more you do it. So your friend is talking about literally the cross-section. And this counts as a cross-section, by the way, this parabola. So the question is this parabola, does this parabola have an a value that's more or less than 0.1 for this 0.1 x squared? So let's first see what this parabola has in store for us. Let's, y equals ax squared. Let's figure out what this one has. This is, I can plug in 3.2 for y and 4 for x. This is where I would use this calculation because I don't know what I have to divide by, I guess, what, 20? 1/20th? Am I saying it right? Maybe I'm saying it the wrong way. No, 1/5. 1/5? 3.2 equals 16 times a, and divided by 16. A is 3.2 divided by 16, which, yeah, I think that's 1/5. So this is, well, sorry, which is 0.2. 0.2. So y equals 0.2x squared is the current parabola that we're looking at. Now compared to y equals 0.1x squared, this one would be more vertically stretched. Not compared to this. So the one that we're looking at, is more vertically stretched than a 0.1x squared. A 0.1x squared would be more like that, or in this case, like that, right? Which means it would have less speed. Your friend claims rotational speed of the water would have to increase for the cross-section to be modeled by 0.1x squared. No, your friend's incorrect. Your friend, so I'll try and explain it through typing. Your friend is incorrect. The cross-section of the current model, of the current swirl is modeled by y equals 0.2x squared. No, x squared. No, x squared. There we go. Which is more vertically stretched than that of y equals 0.1x squared. Now, what does that mean? When water swirls, you would get a more vertically stretched cross section. So swirling it more would increase A, not decrease it. So your friend's wrong. Your friend is wrong. And with that, we will leave it at that. So that is part B. That is the final answer. All right, guys, that ought to do it for this one. So they really do have ways that they can go about explaining some things to you with y equals ax squared only and not do more of it. My key intent, and maybe a lot of teachers' key intent when they navigate through this book, is let's learn to graph these things. So ax squared A is not the only value to talk about, but maybe it's a good introduction to talk about because there's no longer slopes. You might have recognized I never mentioned up 3 over 1, up 3 over 1. We tripled our y values, and the behavior of a quadratic is different than that of an absolute value function, which is just up 1 over 1, which is why there's a slope. These don't have slopes. The u-shapes are a little different. So if you heard what I said here today, and if it made some sense to you, hopefully it can carry on to the other parts when we start to use translations, whether they're horizontal, vertical, or both, because those a values will still permeate. Remember what 1 squared is 1, 2 squared is 4, 3 squared is 9. When it flips over, things like that, that would be very helpful. I see it say Swifty in the background for a Travis Kelce jersey, so that was kind of interesting. All right, guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching, and I will see you in the next one, which will be section 3.2. Take care.